We'll start in a minute. All right. So let me introduce myself. I am Shubham Keshri, and I am currently pursuing my PhD in the Department of Management Sciences, IIT Kanpur. My area of research is operations management, applied operations research actually, and I'll be your TA for this, one of the TA for this course. Um, so this is week 2, and in the last week lecture, we did some problems, and in this week, so the flow of this lecture will be, we will discuss problems, and through these problems, we will understand the concepts which Professor Aditya has taught in his videos in week 3. I would request you to kindly unmute yourself and speak, because the chat option would not be available to you at your end. And please do not hesitate to interrupt me at any time, and you can ask questions from your end. Before I proceed, do you have any doubt in previous weeks' problem sessions or any other issues with the content of the videos which Professor has provided, or any confusion? Do you want to ask something? All right. So I would assume that there is no question. So let us begin. So the first concept which we'll talk about is, so this is a problem called tragedy of commons, and this was discussed in the first and the second lecture by Professor Aditya. And here I wanted to point out one important idea, which is the need of a regulator. All right. So in this problem, tragedy of commons, there is a common resource, which a pool of resource, which few people or few players are using or utilizing, and in that process, that resource is being consumed. So the more people consumes that resources, the resource becomes scarce, and in that way, there is a game being played between the players, how much resource one should use. And I will just go through the whole problem once again, and then we will discuss why there is a need for a regulator. And when we have discussed the concept of this game, then we'll move on to a problem on this concept. All right. So the idea of this problem comes. So the context I have given you. So the example which Professor Aditya has taken was the utility of the player. So for player 1, we'll write U1, and his strategy is E1, and player 2 strategy is E2. This is given by E1 1 minus E1 plus E2. So if you notice, this is the total strategy or total effort both the players are putting. So there are two players in this game, and this sum is being subtracted by 1. So we have an inverse relationship. The more the resource is being used or effort has been put, the less overall resource is available for the players. All right. So this is the utility of player 1. Similarly, the utility of player 2 will be given as, so I'm writing U2, which means utility of player 2. The first strategy is of player 2, and the second strategy represents the strategy of all the other players. It will be E2 times 1 minus E1 plus E2. All right. So these two are the payoffs or utility of the players. Moreover, this utility is continuous in the range from 0 to 1. So it can take any value between 0 to 1. So this is the description of the problem. Now, if you have done the course on calculus, you would know that if you have to minimize or maximize a function, you have to take its derivative and then equate it to 0, the first order derivative, and then equate it to 0. So if you want to maximize the utility of player 1, then you will have to differentiate this utility in terms of with respect to player one's effort. This is what professor has also done in his lectures. If you don't remember, you can just follow me over here. So we'll say del u1 by del e1. So we are assuming that e2 is constant. So in this case, e2 is constant. We'll write this as, so this is actually u into v. And if you know how to differentiate a function of u times v, it will be keep u as it is and then differentiate v with respect to e1. So it will be minus 1 plus keep v as it is, 1 minus e1 plus e2, and then differentiate this with respect to e1, which will be 1. And this will come out to be 1 minus 2 e1 plus, sorry, not plus, minus e2. So it will be minus e2, e1 minus e2. All right. So this is the the equation, the first order derivative, and we'll equate it to 0. When we equate it to 0, we'll say the effort put by the first player will be its best response. Why? Because you see, you are differentiating the utility and you are equating it to 0, such that the utility will be maximum. So when the utility of a player is maximized for a given response of a player 2, that utility is known as best response of player 1. Therefore, we are writing E1 star. And if you solve this, it will come out to be E1 star is equals to 1 minus E2, sorry, E2 by 2. Similarly, since this is a symmetric problem, you will obtain E2 star as 1 minus E1 by 2. Now you see, this E1 and E2 are actually the unknowns of this problem, right? So you cannot just say E1 is equals to 1 by 2 E2 and E2 is equals to 1 by 2 E1. You have to obtain the values of this E1 and E2. And for that, you have to equate these two equations and then solve it. Before doing that, you should know the concept of Nash equilibrium. So you see, this is the best response equation. The best response of player 1 is given as E1 star, and it comes out to be 1 minus E2 by E1. So for this given strategy of player 2, which is E2, the best response of player 1 is 1 minus E2 by 2. Similarly, the best response of player 2 is given by E2 star, which is equal to 1 minus E1 by 2, where E1 is a given value. All right. Now at Nash equilibrium, best responses intersect. All right. This was taught in first week's lecture, where we understood that whenever the best responses intersect, we have a Nash equilibrium. So these points E1 and E2 will become E1 star and E2 star. So it will be E1 star, comma E2 star. So both the players are actually playing their best responses. Both the players are actually playing the best responses. Therefore, player 2 will play E2 star and we can obtain the value of E1 star, and player 1 will play E1 star and we can obtain the value of E2 star. So when we do that, E1 star is equals to 1 minus E2 star by 2, and E2 star is equals to 1 minus E1 star by 2. If you solve these two equations simultaneously, then you will obtain, or we can just do that, I guess. We will just put this value of E2 star over there. We'll get E1 star equals to 1 minus E1 star by 2 by 2. So we have just substituted this value over here, and then we are solving the problem. This will become 2 minus 1 minus E1 star by 4. E1 star is equal to. Now you can just put this E1 star on the other side, and you will obtain E1 star plus E1 star by 4 is equals to 1 by 4, or E1 star is equals to 1 by 4 times 4 by 3, which is equals to 1 by 3. And since this problem is symmetric, you will obtain that E2 star is also 1 by 3. Therefore, 1 by 3 comma 1 by 3 is a Nash equilibrium for this problem. All right. So E1 star comma E2 star becomes 1 by 3 comma 1 by 3. This is the Nash equilibrium. Now, if you are facing any trouble on understanding what we are discussing over here, please unmute yourself and speak. Okay. So when you will communicate what in which area you are facing problems, we can then discuss it further. All right. So this is the Nash equilibrium of that problem. Now, when we can see that if both the players, if there is a coordination between both the players, if both the players work together, then we can obtain a better utility for both the players. And this was discussed in the lecture as well. We will see that if there is a combined effort ET, which is equals to E1 plus E2, then utility of overall utility, so I'll write UO, will become ET times 1 minus ET. All right. And this utility is actually obtained by U1 plus U2, where U1 is given by E1, 1 minus E1 plus E2, plus E2, 1 minus E1 plus E2. If you solve this, it will become E1 plus E2 times 1 minus E1 plus. So we are putting ET as E1 plus E2. Therefore, we are obtaining ET times 1 minus ET. And for this utility, you can just differentiate this by ET, and you will obtain ET times minus 1 plus 1 minus ET, which is actually equal to 1 minus 2 ET. And when you substitute this as equals to 0, you will obtain ET as half. Now, this ET is what? This ET is the combined utility of player 1 and player 2. Therefore, ET1 plus ET2 is equals to 1 by 2. Now, if we assume that E1 and E2 are same, which is a fair assumption to make, both the players are actually putting same effort to obtain that resource, then you will obtain E1 is equals to E2 is equals to 1 by 4. And the utility of these players when the effort is 1 by 4 will be obtained as, so I don't have space, I'll just erase few parts over here. So what I'll do is I'll just take a eraser, just erase this part. So when we obtain the utility for ET as 1 by 4, the combined utility will become 1 by 4. So I will write the expression first. The expression is U0 is equals to ET times 1 minus ET. So the combined utility of both the players will become 1 by 4 times 1 minus 1 by 4, which is actually 1 by 4 times 3 by 4. All right. Is there any confusion till now? Okay, if you don't have confusion, so this is the overall utility, which is 3 by 16. Now you can obtain the utility of individual players. So you can just obtain E1, which is 1 by 4 comma 1 by 4. Over here you can just put 1 by 4 comma 1 by 4. It will become 1 by 4 times 1 minus 1 by 4 plus 1 by 4. And when you obtain this, you will see it is greater than U1 1 by 3 comma 1 by 3. And this 1 by 3 comma 1 by 3 is the Nash equilibrium. So you see that a utility higher than the utility of Nash equilibrium is obtained. And if you remember the definition of Pareto optimality, this is the exact definition of Pareto optimality, where we see that both the players can simultaneously improve their utility at the same time, and hence the Nash equilibrium is not Pareto optimal. All right. So this is what was discussed in the lecture. Now, the additional part which I wanted to discuss over here is why is there a need of a regulator? Why is there a need of a regulator? So you see, I just erase some parts over here, and then we'll discuss. So you see, when we have a regulator, or when we don't have a regulator, the Nash equilibrium is E1 star, comma E2 star. E2 star is 1 by 3, comma 1 by 3. All right. Now we saw that there is one more strategy or combination of strategy which yields a higher payoff, and that is Pareto optimal. That was E1, comma E2 as 1 by 4, comma 1 by 4, and the utility of both the players were higher than what was at Nash equilibrium. All right. Now suppose there is some authority or a regulator which specifies that this will be the effort of the players. So they are saying that the players will have to put an effort of 1 by 2 instead of 1 by 3. What will happen in that case? You see, suppose player 1, so this regulator, what he is doing, he is saying that you have to put a utility of 1 by 4 instead of 1 by 3. So suppose player 1 is actually playing E1 as 1 by 4. Now player 2, we'll see what is the best response of player 2. We saw that best response of player 2 was 1 minus E1 by 2. So suppose player 1 is actually playing how the regulator has set the rules, and regulator is saying that you have to play 1 by 4. Now player 2 can deviate because he has an incentive to deviate. What he will do, he will say that I will play my best response. So he will do 1 minus 1 by 4, where this 1 by 4 is the strategy of first player. This value will be, so the utility, so this is, we are obtaining the action strategy of player 2. This will be 3 by 4 by 2, which is equals to 3 by 8. Now we can see, we can observe that this um, effort or this action yields a higher utility to player 2 as compared to when he would have played 1 by 4. You can just obtain this due to when player 2 is playing 3 by 8 and player 1 is playing 1 by 4. This will be value as 3 by 8 times 1 minus 1 by 4 plus 3 by 8. And if you obtain this, you will get 3 by 8, 1 minus, so this will be 5 by 8. And this will be 3 by 8 times 3 by 8. And the value of this will be, I have just obtained, I can just calculate 8, 3, it will be 9 by 64. So this value is coming out to be 0.140625. All right. And if you remember, the utility at Nash equilibrium, was, is there any question? All right. So the utility at Nash equilibrium was 1 by 8. If you just go back and check the lecture, you will see that the utility was 1 by 8. And this value is coming out to be 0.125. Now you see this is higher than, this value is higher than 0.125, which is the Nash payoff. Moreover, it is also higher than what is set by the regulator. So when players are playing 1 by 4, the utility of the players will become, so we had obtained this, I erased this. So the utility of the players will become U1 as, so player 2, U1, not U, it will be U2. It will be U2, not U1. So U2 is playing, U2, he is playing 3 by 8, and player 1 is playing 1 by 4, and this is, sorry, so both the players will play 1 by 4 at, when the regulator is active. When the regulator is active, both the player is playing 1 by 4. All right. So it will become 1 by 4 times 1 minus 1 by 4 plus 1 by 4, which is actually 1 by 4 times. So this will be half. 1 by 4 times half, which is 1 by 8. All right. So this was actually 1 by 9, I guess. I'll just check. Yes. So this was 1 by 9. And this is 1 by 8, which is 0.125. And you see this value is higher than this value. Therefore, a regulator is required. All right. So this is what I wanted to discuss, why a regulator is required when this type of games are played. So I'll just summarize. I have discussed a lot of things over here, and a lot of things are mathematics. So what we have done, we have seen that the Nash equilibrium payoff is 1 by 9. All right, the Nash equilibrium payoff is 1 by 9. Now you can obtain a payoff which is higher than 1 by 9 if you play the Pareto optimal strategies, and that payoff comes out to be 1 by 8. 1 by 8 is obviously higher than 1 by 9, therefore that is a Pareto optimal solution. What I am saying is, suppose there is no regulator and the first player is playing. So suppose there is a regulator and he is saying play 1 by 4. Now player 1 is playing 1 by 4, but player 2 is saying that I will deviate to the best response I can do. And the best response of player 2 is 3 by 8. Because he's playing 3 by 8 instead of 1 by 2, he's obtaining a payoff of 0.14, which is actually higher than the Pareto optimal payoff. Therefore, player 2 has an incentive to deviate to this strategy, which is 3 by 8 instead of 1 by 4. This is what I am saying. And that is why you need a regulator. If you don't have a regulator, then they will actually move to Nash equilibrium, which has a payoff less than the Pareto optimal payoff. All right. So this is where the regulator comes into play. So this is a question which I have taken from the lectures of Professor Aditya, and I have just modified it. So it says that we have n players and we are playing the game of Tragedy of Commons. So in this game, we have just saw the utility of the player is given as EI. So I'm just write utility of player I, and it is given as EI times 1 minus summation of utility of all the players. So I have written J is equals to 1 to n. This sum is actually representing E1 plus E2 plus E3 plus E4 and so on till En. All right. So this is what I have written over here. And if you see, when we have two players, we'll just write it as EI 1 minus E1 plus E2 for two players. Right. So similarly, for n players, this will be the utility. Now the question is, what is the Nash equilibrium of this game? We have seen the Nash equilibrium when we had two players. Now we are having n players. This is an n player game. And the question is, find the Nash equilibrium of this game. I'll just give you 2 minutes so such that you can solve this problem, and then we'll discuss the solution of the problem. Remember what you have to do. You have a utility function. You have to obtain its first derivative such that you can equate it to 0. When you do that, you will obtain the maxima of this function, which is Qi. And therefore, you can obtain at which value or at which response, the best response of that player, such that the utility is maximized. That is what the best response is. Given the strategy of all the other players, what is the best response of EI? You have to do this for all the players, but since this problem is symmetric, you will see that all the different when you obtain the best response are same for all the players, and then you'll have to obtain the Nash equilibrium. And what is a Nash equilibrium? A Nash equilibrium is a point where all the players are playing its best responses. All right. So these are the hints I have given you. I'll give you 2 minutes. Please think about it and then we'll discuss. All right. So can anybody tell me uh, how did you obtain, or what will be the best responses of the player? You can just unmute yourself and then speak. Okay. So I'll just show you how we can do that. So you see we have n player game. This is the expression of, or this is the expression of the utility. So I'll erase this expression because this is the expression of two players. I'll just erase this expression and then we'll proceed. Okay, so you see UI is the utility of player I when player I plays EI and all the other plays EI minus. This is given as EI times 1 minus summation of j is equals to 1 to n EJ. Now you see in this sum, we have an EI, right? So if you expand this sum, so I'll just expand this sum over here. EI times 1 minus E1 plus E2 plus dot 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 EI minus 1 EI plus 1 plus dot 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 EN, right? So you have a EI in this sum. You can just take this EI out of this sum. When you do that, it will become EI 1 minus EI minus summation of j not equals to I j. So you are summing it up for all j not equals to I. So you don't want to add this because you are just taking that out. All right. Now you can just differentiate this because this sum doesn't have EI. When this sum doesn't have EI, when you are differentiating, it will become 0, right? Because it is independent of EI. So UI is this, and I just differentiate this UI by del EI. So why I'm writing del and not E? Because this utility is a function of all the this utility is a function of effort of all the players. So you cannot write D. We are partially differentiating this utility. All right. So if you have doubt why are we partially differentiating it, we can discuss this. Uh, Otherwise, we'll proceed because this is the concept which is taught in differential calculus. All right. So we are differentiating this utility with respect to the utility of the player I, and what we'll obtain is, so this is U into V, U into V. So this differentiation is given as, so you will just write U as it is and you will differentiate V. So when you differentiate V, this will become 0, this will become minus 1, and this will also become 0. Why? Because there is no EI in this sum. We have taken out. So it was summation of EJ for all J, but we have taken out. So this is all the sum, and we have taken out EI outside this sum. So therefore we have EI over here. We don't have EI over here. So this will also become 0. Plus you write V as it is, 1 minus EI minus summation of j not equals to I EJ, and you differentiate V, which will be 1. When you do that, it will be minus EI plus 1 minus EI minus summation of j not equals to I J. And this is actually 1 minus 2 EI summation of j not equals to I J, right? So this is the differentiation of the utility. Remember, this is a utility function, and to obtain the best response, we have to differentiate this function and equate to 0. That is when you will obtain a maxima of this function. All right. So we'll just equate it to 0. When we equate it to 0, I just use the next slide. So we had an expression ei minus summation of j not equals to I ej. And when we equate it to 0, we'll say the player I is playing its best response. All right. When player I, so you see, we were differentiating the utility of player I, and we are saying that this expression, which is obtained by differentiating the utility, will equate it to 0. And then we'll say this is the best response of player I because we are equating it to 0. This is what Professor Aditya has also done in his lecture. Now, if you do that, you will see that EI star, the 2 EI star will be 1 minus summation of EJ, J not equals to I. And EI star will become 1 minus summation J not equals to I, EJ by 2. Now you see these expressions, E star, are not talking about, um, it shouldn't have EJ because those are also unknowns. You have to obtain those values. So what we'll say that the utility of all the players are same. So E1 is equals to E2 is not utility, I'm sorry, the strategies or the efforts. So in the tragedy of common, when Professor Aditya was also discussing, he also assumed that E1 is equals to E2. So over here also we'll say E1 is equals to E2 is equals to dot 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 till En, and we'll say it is equals to E. All right. So this is not a this is a fair assumption to make because we are saying that whatever players are over here, they have to put in the same effort for the common resources. To obtain the utility from the common resources, you have to put the same effort. That is why we are saying the utility of all the players are same. And when you put this in this expression, you can just solve it very easily. So this will be E star is equals to 1 minus. So this sum is actually, how many terms are there in this sum? You just see. We had first summation of j is equals to 1 to n ej, but we are saying that j shouldn't be equal to I. So therefore we had n minus 1 terms in this sum. If you say j not equals to I, you are eliminating one of the terms in this sum. And how many terms were there in this sum? From 1 to n. So there were n terms, but you are saying j shouldn't be equal to I. Therefore you are eliminating that one term. So there are n minus 1 terms in this sum. And when ej is all the ej's are same, so this sum will become n minus 1 times e. So it will be n minus 1 times e by 2. And then you can just solve it. It will be 2 e star is equals to 1 minus n minus 1 by 2 into e. Now you see this is the best response of a player. Whenever all the players are playing the best responses, that is when we obtain the Nash equilibrium. So we will say this E is actually E star. So all the other players are actually playing their best responses, and that is when we obtain the Nash equilibrium. So 2 E star is equals to 1 minus n minus 1 E star. And if you solve it, this will come over here, 2 E star plus n minus 1 E star is equals to 1, and just I'll write it here. So you see, you can just take out E star 2 plus n minus 1 equals to 1, and this is just n plus 1. So E star is equals to 1 by n plus 1. So this is the solution of a problem which is tragedy of commons, but we have n players. In the lectures, we had discussed the same problem with the same utility function for 2 players. You see, this is a utility function of n players. We have two. When you have 2 players, ei comma e minus I, you will have ei times 1 minus. So this sum will have 2 terms, e1 plus e2. So this is the exact problem which we had, which professor has discussed in the class. I had just extended this problem to n players, and therefore we have obtained the Nash equilibrium for this problem. And the Nash equilibrium for this problem is this expression, when all the players are playing the same response, which is 1 by n plus 1. So this is the solution. This is the answer. All right. Any doubt? So Mukesh, I saw you have joined late. If you have doubt in this question, we can just repeat it again for you to understand. Is it all right?
No, I was just DUI by DEI. In that term, you have taken EI as a bracket outside, right? But when you do it, EI into -1 is coming. That first term, I was not able to get it. You've done a differentiation of A into B, and then that's how you've done it, right?
Yes. U into V.
That's the formula you've done. A into B, wala kiya hai. Okay,
So
okay,
I have,
fine.
right?
So, but why is that -1? Because when you take the first term, in differentiation of EI will be EI into 1 only, na?
No, you see, when we differentiate U times V, it will be U into differentiation of V plus V into differentiation of U. So I have written U over here. This is the differentiation of V. So when you differentiate this, it will become -1. This EI
Acha,
will become
0
minus
minus
1,
1 and then, okay.
0.
Yeah, understood.
And again for this term also, you have just written V, and this is just differentiation of U.
Yeah, okay, understood. Yeah.
Right? And then how we have solved it, and then assuming that all the efforts are same, and then we have obtained the
Yeah,
Nash
I got that.
equilibrium. All right. So this is another problem in battle of sexes. So this professor has discussed in great length, and why I have taken this problem again is because in your assignment you have this problem, and there are few things I wanted to discuss again. So I have changed the utilities of the players, and we are saying that there is a girl and a boy which has two strategies. Either they can go for a cricket match or a movie. So you see how we have played with the utility over here. We are saying when the boy is going, so this is boy and this is girl. When the boy is going for a movie and the girl is going for a cricket, so the girl doesn't like cricket and boy doesn't like movie. So both the utilities will become zero. But when boy and girl both go to cricket, the girl sees that the boy actually like cricket. Therefore, she has some positive utility, and obviously, boy like cricket, then he has a higher utility. Similarly, when boy go for a movie and girl go for a movie, boy likes movie but he likes cricket better. Therefore, the utility is a little less one, and since both of them are in disagreement, therefore girl's utility is also less. But when the girl go for a movie and boy also go for a movie, the boy's utility is a little higher and girl's utility is highest. Alright. So this is how I have played with the numbers. These are just numbers. The utility is obtained from other concepts. So we'll just obtain. So this question asks me that the girl is actually playing a mixed strategy. This strategy is 1/3 of the time she is playing cricket, and 2/3 of the time she is playing movie. So what is the best response of the boy? This is what the question is. All right. So the girl is playing 1/3 and 2/3. So what should be the best response of the boy? Best response of the boy. This is the question. So before moving on to such concepts, you should know the steps. What you have to do is you have to obtain the utility of the players when they are playing individual strategies, and then you can obtain the best response. And once you have obtained the best response, you can then move on to the Nash equilibrium. So this is just a problem where you have to obtain the best response. So before obtaining the best response, you should know what is the utility of the player. So you have to obtain the best response for the boy. Therefore, you have to obtain the best response utility of the boy. So utility of the boy when he is playing cricket, and going for a cricket match, and utility of the boy when he is going for a movie. Please try to obtain these values. Then we'll discuss. And if you have already done it, you can just unmute yourself and speak. Is there any confusion or doubt? Okay, so do you want to speak up and let me write the utility, or should I just move on? Or I should write the utility?
I think the boy's utility when he's playing cricket will be 1 plus 2/3, so 1 2/3, right? So 4/3. And
Right. So it will be 1/3 times 3. So this is the utility. He's
1
getting it
plus
1/3
2/3, yeah.
plus 1 into 2/3. Okay. Similarly, over here it
Yeah,
will
so
be
1,
0 times 1/3 plus 2/3
correct,
times
yeah,
2.
yeah.
Right. So it will be 4/3 over here, and this will be 1 plus 2/3, which is 6. 1, 3, 5/3. All right. So these are the
Yeah.
utilities when boy is going for a cricket and or movie. So now tell me, what is the best response of the boy? Should he play pure strategy or should he play a mixed strategy? That is also a question over here. Because this best response can also be a probability. You have seen this in mixed strategies, and we'll discuss it after this.
No, he doesn't have a pure strategy over here, right? A pure dominant strategy he doesn't have, so he will have to play a mixed strategy, right?
Why should that be a case?
That's because when the girl chooses cricket, 3 is greater than 0, and when the girl chooses movie, 2 is greater than 1. So he's not having either cricket or either movie as a dominant one. So is that
Right.
right?
So this is this confusion I know student may have. That is why I have kept this question. You see,
Acha.
the strategies of the second player, the girl, has already been shown or shown to the us or the boy. So he knows that girl will either go for cricket 1/3 of the time and movie 2/3 of the time. So he know exactly that this will be the utility if he goes for cricket, and this will be the utility if he go for movie. Right? The boy has this
Yeah.
knowledge that this will be the utility if he goes for cricket, and this will be the utility if he goes for movie. So his strategy will be the best response. What will be his best response to maximize his utility? In which, so what should be the probability that his utility is maximized? You see, if he's playing cricket with P and 1 minus P as this movie, you see, if this P is equals to 1, his utility is maximum. What is his utility? You see, it will be 5/3 times P plus 4/3 times 1 minus P. Right? This will be his utility. And when he plays P as equals to 1, then his utility is maximum. Because it is 5/3 and not 4/3.
Yeah.
Right? So he has to play, he will play a pure strategy, which is always cricket. He will always go for cricket and not movie. So the boy will play a pure strategy, but the girl is playing a mixed strategy. And we will see this next when we discuss this battle of sexes again in detail. So is this clear or you have some doubt?
No, I'm just processing. What you're essentially saying is because of this formula P and all that, you're anyway getting P equal to 1 and hence cricket. But logically, if I check, if he always plays cricket, he's getting some utility or the other, at least 3 or 1. Maybe it is because when he plays movie, the first one is 0. Is that
Yes,
how was it playing out?
yes, yes, yes.
Yeah.
So it
Okay.
is not because this is 0 or this is 2. It is because the utility when he plays movie is 4/3 because of the strategy of the girl. So
Yeah,
these
yeah, yeah,
numbers are
yeah.
important. These numbers, not these numbers. So we have
And
obtained
5
this
by
number
3 is
from
greater
this.
than 4 by 3, and hence,
Right,
since
right.
5 by 3 is greater than 4 by 3, and hence. Okay.
Yes, yes.
Okay. Okay.
All right. So
Yeah.
we'll just discuss Battle of Sexes again. Then we'll have. Okay, so I have written what is the Nash equilibrium. So you see over here we are saying that this is boy and this is girl, and the boy is playing cricket with a probability P and 1 minus P movie, and similarly girl is playing cricket with Q and 1 minus Q as movie. All right. So what is the steps? Always remember the steps. Obtain the utility of the players, then maximize those utilities, and then obtain the best responses for each player. And whenever the best responses intersect, that will be the Nash equilibrium. These are the steps to obtain a Nash equilibrium, either pure or mixed, doesn't matter. These are the steps. All right. So you see, let me go through this question because I want to discuss few things, and then you will see some interesting observations. All right. So you see, utility of boy. We'll just see first the utility of boy when he plays cricket. Utility of boy when he plays cricket is 3Q plus 1 times 1 minus Q. So by the way, if I make any mistake, please point it out. All right. So utility of boy when he plays movie is So this will actually become 2q minus 1. And this is 0 times q plus 2 times 1 minus q, which is actually 2 minus 2q. Now, you see, this is the utility of player of boy when he plays cricket, and this is the utility of boy when he plays movie. Now, when this utility becomes same, in this problem you have seen that when the utility of one of those is larger, he will always play that strategy. So if utility of movie was higher, no matter what the utility of cricket is, since it is lower, he will always play movie. So if these utilities are the same, then it is indifferent for him. So suppose the utility of this cricket is anything, suppose it is 7, and utility of movie also comes out to be 7, then boy will be indifferent of playing either cricket or movie. But since the utility of cricket is higher than the utility of movie, he will always go for movie. So for the boy to be indifferent in both the strategies, either cricket or movie, these two utilities will equate as same. So we'll say 2q minus 1 is same as 2 minus 2q, which will become 4q is equals to 3 and q is equals to 3 by 4. All right. So this is that strategy of the girl when this boy becomes indifferent of its strategy. Now you see we can obtain the best response of player boy. So this will be given as P star. All right. What is the best response of this player? So we can divide it in 3 parts. We can say if q is less than 3 by 4, if q is greater than 3 by 4, if q is actually equals to 3 by 4. All right. We have 3 parts in this this strategy of the boy. You see, when this q is less than 3 by 4, when q is less than 3 by 4, then what is the utility of the boy? You see, suppose the utility q is any value less than 3 by 4, suppose it is half. So this will become, so UB cricket will become half, so it will become 0, and UB movie will become, so it will be half 1. So you see, utility of movie is becoming 1. So whenever q is less than 3 by 4, he will always go for movie. So p will be 0. When p is 0, then 1 minus p is 1. So we will always go for movie. In the same thought, when q is greater than 3 by 4, when q is greater than 3 by 4, suppose we are taking as 1. So when q is equals to 1, you see u of bc will become 2 minus 1, which is 1, and this is 2 minus 2, which is 0. So you see, when q is greater than 3 by 4, that is when utility of cricket is higher than utility of movie, he will always go for cricket. And when the girl's strategy is such that boy's utility becomes same for cricket and movie, he can take any value. He can take any value between 0 and 1. The strategy can be any value. Is this all right? Because this is a very important concept to understand. You see, the utility of the boy actually governs his strategy. This utility gives the best response, and now we have not obtained the Nash equilibrium, we'll obtain the Nash equilibrium. So till now we have obtained the best response of boy. Is this all right?
Just 1 minute. In that P star equal to 0 when Q is less than 3 by 4, I understood. Why are you calling it 0? The strategy of choosing a movie is called a 0, is it?
No. You see, P is the probability of choosing that movie. So when P is 0,
okay, P is the probability of choosing cricket. So the probability of choosing cricket is 0. Okay.
Right. You'll always go for movie.
Okay, understood. That is the interpretation. Yeah.
So this is the best response table for boy. Similarly, we can obtain a best response table for the girl. All right. Before going to that, we can just draw a diagram. All right. And I'll use this diagram. So I'll just draw this diagram over here. So this was discussed in the lecture. All right. So I'm not doing something special. It was just, I'm just reiterating it. So you see, we are actually on this, we are actually talking about the strategy of boy. So we are actually worried about P. Now you see when Q is, so I'll just mark 1 by 4, 3 by 4, and 1. Similarly, 1 by 4, 3 by 4, and 1. Now when Q is less than 3 by 4, P is always 0. So when Q is less than 3 by 4, so this value I'll just take another color. So when Q is less than 3 by 4, P is always 0. So this is the line which says when Q is less than 3 by 4, P is 0. You see, at this point, P is equals to 0. All right. Now it says then when Q is greater than 3 by 4, P is 1. So when P is 1, so this is the point when P is 1. You see, I'm just drawing like this. All right. So when Q is greater than 3 by 4, and it will always, obviously it will never be more than 1 because it is probability. So when Q is between 3 by 4 and 1, P value is 1. And when Q is actually 3 by 4, exactly equal to 3 by 4, P can take any value between 0 and 1. Therefore, it can take any value. So this is the exact line or function of the best response of player 1. So this line actually depicts best response of boy. Whatever value you give, you can obtain the best response of boy. All right. So we'll come back to this when we talk about the best response of girl. Any doubt in this diagram or graph?
No, I'm clear.
All right. Now we'll move on. So I will just write the table over here for some easiness. All right. So it is 3 by 3 comma 2, 1 comma 1, 0 comma 0, and 2 comma 3. Cricket, movie, boy, girl. Alright, so this is the table. Now we are saying that this is P, this is 1 minus P, this is Q, this is 1 minus Q. Now what are we saying? We are saying that you have to obtain the utility of girl when she is playing cricket and utility of girl when she is playing movie. What is the utility of girl when she is playing cricket? You see, boy is actually playing the strategy P for cricket and 1 minus P for movie. So it will be 2P plus 1 minus, not 1, it will be 0. Sorry. It will be 2P plus 0 times 1 minus P. So it will be 2P. Similarly, when girl is playing movie, the utility will become 1P plus 3 times 1 minus P, which is actually 3 minus 2P. All right. Now again, we'll have the same logic over here. We'll apply the same idea. What are we saying? We are saying that when this utility of the girl for both the strategies becomes same, this girl will be indifferent of playing either cricket or movie. So when it is 2P is actually equals to 3 minus 2P, which is have I done some error? No. 4P is equals to 3 and P is equals to 3 by 4. So this is that point. This is that strategy of boy at which the girl become indifferent of playing cricket or movie. So let us see best response table for girl. We'll write it as Q star. All right. We'll have 3 parts again. When P is less than 3 by 4, if P is greater than 3 by 4, and if P is exactly equal to 3 by 4. Right. So this is how we'll this is how we'll write. So when P is less than 3 by 4, so you see this. So suppose take any value, take half. So when P is actually half, so it will become 1, and when P is half over here, it will become 2. So you see, girl will try to go for a movie. Therefore, Q will become 0. So when P is less than 3 by 4, girl will always go for movie. When P is greater than 3 by 4, suppose we are taking as 1 for simplicity to understand what is happening. So this will become 2 and this will become 1. In that case, you see, girl will always go for cricket because her utility for cricket is higher. And again, for this case, when the boy is playing 3 by 4 as the strategy, the girl will be indifferent of playing any value between 0 and 1. She can take any value. Now we can just plot this again. When P is less than 3 by 4, it is 0. When P is less than 3 by 4, I'll take another color. So when P is less than 3 by 4, Q is 0. When P is greater than 3 by 4, Q is 1. So this is 3 by 4. And when P is exactly equals to 3 by 4, girl can play any strategy between 0 and 1. So this will be the line. This is the, what is this line? This is actually best response line of girl. So you see, we have obtained the best response of girl and best response of boy. What is a Nash equilibrium? A Nash equilibrium is that point where best responses of the players intersect. So where are best responses intersecting? At this point, and at this point. And now if you go back, you will see that there are two pure strategy Nash equilibrium and one mixed strategy Nash equilibrium. You see, for this game, if girl is always playing cricket, the best response of boy is to play cricket. And when girl is always playing movie, the best response of boy is to play movie. Similarly, when boy is always playing cricket, the best response of girl is to play cricket. And when boy is always playing movie, the best response of girl is to play movie. So you see, this is one Nash equilibrium, this is another Nash equilibrium, and there is one hidden Nash equilibrium, which is actually the mixed strategy Nash equilibrium. So this is one Nash equilibrium, this is another Nash equilibrium, and that is the mixed strategy Nash equilibrium. And you can just relate this point. You see, this Nash equilibrium is when P is equals to 1 and Q is equals to 1. So this is that point, cricket, comma, cricket. This is that Nash equilibrium when P is equals to 0 and Q is equals to 0. So you see, this is 0, 0 and this is movie. And this is the point where P is equals to 3 by 4 and Q is equals to 3 by 4. So these are the three Nash equilibriums in this problem. Any doubt or question?
No, I'm fine. No what others.
All right.
I'll just quit from here and join from a PC. Okay, it'll just take a second.
Okay, no problem. So this is a game. This is matching pennies game, and I have modified the values. Same game. So instead of 1, I have just replaced it by a value 5. And why I have done it, because this is one of your assignment problem. I cannot solve the same assignment problem, and that is why I have modified the values. Why have I done so? Why I have taken the same problem as your assignment problem? This is because this graph which we have drawn for this problem, battle of sexes, this graph will be a little bit different for this problem, matching pennies. It will be very interesting to see how that graph or best responses curve intersect when we have this problem, matching pennies. Right? So this is what we'll see. So you can unmute yourself and tell me how we'll proceed with this problem. So we'll just say player. Okay. Take another color. Player 1, player 2. So utility of player 1 when he plays head, and utility of player 1 when he plays tails. This is P, 1 minus P, Q, and 1 minus Q. Similarly, utility of player 2 when he plays heads, and utility of player 2 when he plays tails. Could you help me out?
In 5 into q plus 5 into 1 minus q. Sorry, minus 5 into 1 minus q.
Right. Similarly, this will become minus 5 times q plus 5 times 1 minus q. We just solve it. So this will become 10q minus 5, and this will become minus 10q plus 5, and we'll just solve it. Before that, utility of player 2 will become um, this will become minus 5 times p plus 5 times 1 minus p. So this is actually minus 10p plus 5, and this will be 5 times p plus minus 5 times 1 minus p. So this will become 10p minus 5. Yes. So you see, this is a symmetric game. If you solve one, you will obtain the other. That is why I have written all the utilities in one page only. So you see, this is the same problem or similar problem to what we have done just now. We are saying that player 1 will be indifferent of playing head or tail. At what point? At what strategy of player 2, player 1 will become indifferent? So in that case, the utility of player 1 will be same. So we'll say 10q minus 5 is equals to minus 10q plus 5, which is actually 20q is equals to 10, or q is equals to half. And if you solve this also, it will be q is equals p is equals to half. All right. Same as previously, it will be minus 10p plus 5 is equals to 10p minus 5, and 20p is equals to 10, and p is equals to half. All right. So this is, so we can just see a mixed strategy Nash equilibrium very easily. The mixed strategy Nash equilibrium is half comma half, again half comma half. Right. But this is what I wanted to convey with this example. This is very simple. This is the mixed strategy Nash equilibrium. Let us see if there is a pure strategy Nash equilibrium in this game or not. So if you see player 2 is playing head, what is the utility of player 1? It is 5 when he plays head, minus 5 when he plays tails. So this is his best response. Alright. When player 2 plays tail, this is his best response. You can just quickly check. When player 1 is playing head, the best response of player 2 is this tail, and when player 1 is playing tails, the best response of player 2 is actually head. So you see, there is no combination of strategies at which the best responses intersect. So there is no pure strategy Nash equilibrium in this game, but there is a mixed strategy Nash equilibrium in this game. All right. So let us draw the graph. Before that, you have to write the sorry. Okay. So let us write the best response of player 1, which is P star. Yes, which is P star. What will be P star? So if Q is less than half, if Q is greater than half, and if Q is equals to half. This is one. Again, best response of player 2 will be Q star, which is actually equals to if P is less than half, if P is greater than half, and if P is equals to half. All right. So let us come to this. When Q is less than half, what is the response, best response of player 1? You see, you come here and just take any value less than half. Let us take 0. So when Q is 0, this utility will be negative, but this utility will be positive. Therefore, player 1 will always try to play tails. That is, P will be 0 in that case. All right. So you can just see what I am saying again. When Q is less than half, so let us take any value. Suppose we are taking 0. So when Q is 0, this utility is negative, this utility is positive. Therefore, player 1 will play tails because he is getting a positive utility or higher utility than what he will get when he plays head. Therefore, this value will be 1 or P will be 0. So P is 0. Similarly, when Q is greater than half, The utility of this will be higher than the utility of this, and therefore player 1 will always play heads. You see, take any value, take 1. This is positive and this will become negative. Therefore, this is 1. And when q is equals to half, this player 1 will be indifferent of playing head or tail. Alright, so same will be for player 2 also. Let us quickly do that. When p is less than half, let us take 0. So when this is 0 and this is 0, so this will become positive and this will become negative. Then player 2 will play heads. Again, p. When p is less than half, we are taking a value of 0. So you see, this is positive, this is negative. That is, player 2 will play heads. That is, q is 1. So therefore, this will be 1. If you check for p greater than half, this will become positive and this will become negative. Therefore, q star will be 0, and over here, player 2 will be indifferent of playing any strategy, either head or tail. Now let us draw this graph. It is interesting to see what happens over here. This is p, this is q, this is 0. So I'll just draw half and 1. These two values again, half and 1. Alright. Now when I'll take a different color. When q is less than half, p is 0. When q is less than half, p is 0. Alright. When q is greater than half, p is 1. For this point. And when q is half, p can take any value. Alright, so this is the best response of player 1. Now, best response of player 2. I'll change the color. I'll take this color. Take this color. So you see, when p is less than half, this part, q is actually 1. Q is actually 1. Is the point. Alright. When p is greater than half, q is 0. So this is the point. When p is greater than half, this part, q is actually 0. And when p is exactly half, q can take any value between 0 and 1. So you see, we had seen over here there is no pure strategy Nash equilibrium, and you see, when these two values are there, then we have pure strategies, either 0 0 or 1 1, and you see, best responses do not intersect at these points. So we don't have a pure strategy Nash equilibrium. Best responses only intersect at this point, that the strategy is half comma half, or again half comma half comma half comma half. All right, it doesn't matter, but you can see from this graph, the best responses only intersect at a point which is a mixed strategy Nash equilibrium, and there is no pure strategy Nash equilibrium. Is this all right?
Yeah, very interesting graph actually.
I'm glad you liked it. Okay, I don't know why I have written the same problem. So we'll move on. So this is one problem where we have an advertisement game. So there are two firms, and they can advertise using campaign A or campaign B. Right? So both the firms has the same strategies to play. First, you have to find out what is the pure strategy Nash equilibrium. You can quickly do that. Pure strategy Nash equilibrium. So this is player 1 and this is player 2. So this is also a very interesting example for mixed strategy Nash equilibrium, and we'll see why this is interesting. You see, in the first problem, we had 3 points, 3 Nash equilibriums, 2 pure strategy Nash equilibrium and 1 mixed strategy Nash equilibrium. In this problem, matching pennies problem, we had no pure strategy Nash equilibrium but 1 mixed strategy Nash equilibrium. And in this problem, something more interesting we'll see. All right. So before that, we'll just see what is the pure strategy Nash equilibrium for this game. Anyone can quickly unmute and just speak. Roshni, I see you have joined just now. So if you don't understand, you can just interrupt me anytime. All right. Hello.
Pure one seems to be BB.
Pure one seems to be BB. Okay, so we'll just go through. So yeah, we have read. So when player 2 is playing A, so the best response of player 1 is B. When player 2 is playing B, the best response of player 1 is actually B. Again, when player 1 is playing A, the best response of player 2 is this part B, and when player 1 is playing B, the best response is this. So this is the pure strategy Nash equilibrium. And if you look very closely, this is the same problem as prisoner's dilemma. Any doubt in that? Why this is same as prisoner's dilemma? You see, this strategy, this combination of strategy is better for both the players. Just like confess, confess. But the Nash equilibrium says that this is the Nash equilibrium. All right. So we have found out the pure strategy Nash equilibrium. Again, one more problem. What you have to do is, it is saying that firm 1. So I have written player 1. Let us call it firm 1 and firm 2. So firm 1 is mixing A and B with probabilities 1/3 and 2/3. So it is playing 1/3 and 2/3 respectively. What is the payoff for firm 2 for choosing A and B? So you have to obtain payoff for firm 2. Firm 2 when he is playing A, and payoff of firm 2 when he is playing B. Quickly find this out. And Roshni, if you don't know how to do this, then you can just unmute yourself. We'll just walk you through. Can you obtain the utilities? I'm not able to hear you if you are speaking something. You are not audible actually. All right. So could you help me with the utility of player 2?
For A, it is 50 by 3 plus 2
50
into
times
20
1
by
by
3
3 plus
20 into 2 by 3.
Just a minute. Yes, plus 20 into 2 by 3. And this will be
80 into 1
20.
by 3. No, 80 into 1 by 3. No?
Just a minute. So player 2 is playing B. Okay, 80. Yes. It will be 80 into 1 by 3 plus
30
30
into 2
into
by 3.
2 by 3. So you can just obtain these values, whatever these values are. Doesn't matter for this problem. Okay, you can just find out. But again, doesn't matter for this problem. What are we more interested in? We are more interested in finding out the mixed strategy Nash equilibrium in this game. So by the way, this is the solution of this second question. All right. So when you obtain these values, that is what the solution of problem B is. Now, this is more interesting. Find the mixed strategy Nash equilibrium if it exists. I have given a clue. So let us find out. So suppose the player 1 is playing P, 1 minus P, and Q and 1 minus Q. Correct? So utility of player 1 when player 2 is playing. So utility of player 1 when he is playing A will be 50 times Q plus 20 times 1 minus Q. Utility of player 1 when he is playing B is, again, I shouldn't do this. You should speak up and then we'll discuss it together. Otherwise, it's just me giving you
Yeah,
the
okay.
solutions.
80 cube plus 30 into 1 minus
80Q
Q.
plus 30 into 1 minus Q. So if we solve this, what will be the values? 30Q plus 20. And what will be this value?
50Q plus 30.
50Q plus 30. Now, again, with the same discussion which we
If these
had,
to become indifferent, you equate the two.
yes, 30Q plus 20 must be equals to 50Q minus 30, which
Plus
will
30.
actually come out Yeah, plus 30, it will be 20q is equals to minus 10. Q is equals to minus half. What does it mean?
This cannot be minus, no?
Yes. A probability.
No, is there a sign mistake? 1 minute.
Check.
Hello.
Yes, Roshni, you are audible now.
Oh, okay, fine. Yeah. We can go to the next question. I got this question.
So we are talking about problem C now. All right. So we are saying that yes, you are audible.
Okay, fine. Thank you.
So I'm saying
So
that
utility of utility 1 when he plays B, it is the sum is 80q plus 30 into 1 minus q, so equal to 50q minus 30 होना चाहिए ना?
How?
नहीं, 1 second. Sorry. Okay. हाँ, plus 30. Okay.
Plus 30, right? So Roshni, where are we stuck right now? What we have done is, you see, this is same as what professor has discussed in the lecture. If you have seen, you can just follow it quickly or easily.
Yeah. Okay. Yeah, it is not possible. Okay.
So what we are saying is, player 2 has a strategy q and 1 minus q, and utility of player 1 when he plays A is, so you will have to multiply this q with 50 and 20 with 1 minus q. So 50q plus 1 minus q times 20. This is what utility of player 1 is when he is playing A. Similarly, utility of player A1 when he is playing B will be 80 times q plus 30 times 1 minus q. So this is the utility of player 1 when he is playing B. And now what we are saying is, this value of q, that value of q at which player 1 becomes indifferent of either playing A or B, we have to obtain that value. So what are we doing? We are doing equating both the utilities and saying that when the utility of both the strategies will become same, player 1 doesn't matter. He can play either A or B because both the utilities are same. Therefore, we are equating it and we are seeing that this q is coming out to be minus half. And this, since it is a probability, it cannot be minus half, and therefore there is no mixed strategy Nash equilibrium for this game. All right.
Yeah.
There is only one pure strategy Nash equilibrium for this game, and no mixed strategy Nash equilibrium. So only one Nash equilibrium. So before this, we had some problems. In this problem, we had, so you can see we had 3 Nash equilibriums. 1, 2, and 3. For this problem, we have only one Nash equilibrium, which is the mixed strategy Nash equilibrium. And for this problem, we have only one Nash equilibrium, which is the pure strategy Nash equilibrium, and no mixed strategy Nash equilibrium.
Why should the payoff? Okay, we are. How are you saying that the payoffs of a single player should be equal during
right? So we had discussed this some time back. So you see, what are we doing? We are saying that this is the utility of player 1 when he plays A. That is coming out in terms of some q, which is the strategy of player 2. Again, u1b is utility of player 1 when he is playing B. Now, what is the logic? The logic says, okay, she has left. Again, all right.
So the answer is that they should not be. They should be in. Sorry, he or she should be indifferent between playing A and B. That is the answer, right, to that question?
Yes. So why are we doing it? Because we have to obtain the whole range of
the whole range of responses.
Best responses. Yes. See here. So can you hear me, Roshni?
Hello.
Yes. Am I audible?
I'm not able to hear anything. I think there's. I'll check it later in the recording.
All right. No problem. No problem. Okay. So yes. So we have discussed this. Now, can we just think why this problem has no mixed strategy Nash equilibrium, and why this problem has a mixed strategy Nash equilibrium, or for say this problem? So you see over here in this problem, there is one Nash equilibrium which will always be obtained. So in the previous problems, there were multiple Nash equilibriums, and the utilities were such that when a player is playing mixed strategies, then one of the utility will become higher than the other, right? That is how the probability is coming. So when a player is playing some other strategy, that strategy has some higher utility. But in this problem, there is a dominant strategy. Whenever there is a dominant strategy, then you will not have the other strategy will have some probability, because this B, we had discussed this in our last discussion lecture. This strategy B is a dominant strategy. So similarly, this B for the second player is a dominant strategy. Whenever there is a dominant strategy, mixed strategy, Nash, whenever there is a dominant strategy for both the players, then there won't be a mixed strategy Nash equilibrium. All right, because there is no incentive for the player to play the other strategy. We have a dominant strategy. Any questions?
So in that case, what you're saying is, I mean, the moment we see that there is one dominant strategy for both the guys, then there is no need to do attempt that even if there is a question of C, there is no need to even look at and do all this PQ stuff. Like we can immediately conclude.
You see, when there are two players and both have a dominant strategy, then there won't be any Nash equilibrium. But there's a word of caution here. So we have two strategies. There can be 3 strategies, 4 strategies, and so on.
Yeah. Okay.
When you have multiple dominant strategies, suppose you have 5 dominant strategies and there were 10 strategies. Amongst those 5 dominant strategies, you can have
there will be a mixed. Understood. But if there is a single dominant for both, then it will not be.
Yes.
Both or whatever 3.
Yes.
Understood.
Okay. So this is an interesting problem. Okay. This is an interesting problem.
So you're making all these annotations. You will save the file with the annotations, right?
Because yes, when you upload shared a file with the annotations last time. I'll just do that. Do the same.
You will save it. Yeah. Last time means when was it last time?
Last week, Friday. First discussion was held.
The first discussion was on this Tuesday.
No, there are 2 TAs for this course. My discussion is on Tuesday, and the other TA discussion hour is on Tuesday. So this is my second discussion hour.
Achha, so then I think I missed that. We didn't get a mail for that, and I have not seen that recording also, the last Friday wala.
So I have uploaded the recording in the that Google Sheet. You can just go and watch it.
Okay, I'll see. Okay, yeah.
Okay, so this is an interesting problem. This is a little bit complicated. That is why I have kept it at the last. And my apologies. I have written it as S. So you can think it of as A. So what is S? S is a strategy. So earlier we had taken it as A1, A2, A3, or in Tragedy of Commons we had taken it as E1, E2, E3. Here I have written it as S. All right. So this is a community. So if you were not there in the initial part of this discussion, we had discussed this part where we had Tragedy of Commons with N players. Right? Oh, you had joined that time, right? So this is again same problem, but the utility is a little bit different than what it was in the earlier part. You see, the utility of the player UI is actually SI minus 5 by N S1, S2, dot, Sn. Now this is the utility of individual player I. The question is to find Nash equilibrium when N is less than 5, N is greater than 5, and you can also take N is equals to 5. I have not written it because some more concepts will come. But you see, this utility actually depends on how many players are there. Not only the summation of their utility, this N comes in the denominator as well. So some interesting things will happen over here. All right. So let us proceed. We can do this using differentiation as well, or we can just do it in a different way where we don't use calculus at all. All right. So you can do it any way. But you see, if you do a differentiation, you are assuming that the strategy is continuous. It is between a range. But this strategy can only take 2 values, either 0 or 1. In that case, if you differentiate and if you obtain a value of S which is not 0 and 1, then whatever you have done was fruitless. It was not fruitful. Therefore, we have to come up with some ways of obtaining the utilities of each player with these two strategies. And this we are doing till now for all the other problems. You see, for these problems, we knew strategy of player 1 can either be A or B, and we exactly knew the utilities of that players. We didn't do differentiation to obtain the maximum utility or the best response and so on. So those ideas will be used over here when we have n players. So this is a different question than what we have done till now. All right. So any doubt? Sorry.
No.
So how?
If you were to differentiate this, you would have differentiated. I mean, if you would have differentiated with respect to SI.
Right. So you see, this UI is a function of all S, S1, S2, S3, Sn. So when you differentiate, you will partially differentiate this with respect to S1 or Si, right? You are assuming that all the other strategies are fixed, and therefore you are partially differentiating this utility function. You get it, right?
So then here you will get equal to 1 minus everything else is fixed, so it will be 0, right? It will just be 1 or no?
No. This is 1 minus, so there will be one Si over here as well, right? So 5 by n, this will be 10.
Okay. Okay.
So what I'm saying is, since this problem is not continuous, you shouldn't differentiate. This problem is not continuous.
Yeah, understood. Okay.
S can either take 0 or 1. So how will we proceed? So what have we done till now? You see, whenever we have utilities, we have to obtain the utilities for the strategy. So when we have discrete strategies, over here the strategies are discrete, we have to obtain the utilities for both the strategies, and then we'll see what is the best response of that player, right? And then for all the players we'll see, and then the intersection of best responses will give a Nash equilibrium. Any doubt in this discussion?
Okay, effectively you will be making that matrix of values.
It is difficult to make n cross n matrix.
Achha.
Actually, it's impossible to make it in our space. So we'll just, since this problem is symmetric, you can just go on to do this very easily. You see, when ui will say si is 1, so you know we can write it as ui si comma s minus I. So this is the strategy of player I, and this is the strategy of all the other players. So it will be, we can either take, so Si can either take 0 or 1. So we'll just see what happens when it takes 0 and what happens when it takes 1. So we'll say all the other players are playing some strategy we don't know, but it is fixed. And this player I is playing 0. So what will happen? It will be minus 5 by n, and this sum will be S1, S2 dot 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 Si minus 1 plus Si plus 1 plus dot 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 Sn. Any doubt?
Understood.
Okay. Now we'll do this for just 1 minute. Yes. So we'll do this for this as well. For utility, the strategy when it is 1. So we'll do Si minus 1. Now when Si is 1, it will be 1 minus 5 by n. Again, we'll have S1, S2 dot 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 Si minus 1 plus 1. So we'll just take this one out and say Si plus 1 plus dot 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 plus Sn plus 1 times minus 5 by n. Any doubt? So I've taken this Si outside. What I'm doing is, I'll just write clearly. So what I'm doing is, over here I'm just segregating Si minus 5 by n Si minus 5 by n summation of j not equals to I Sj. So in this sum I'm taking out Si, and that Si is coming over here, minus 5 by n. So this will become n minus 5 by n Si minus 5 by n summation of j not equals to I Sj. Any doubt?
No.
Any doubt?
No.
I hope it is clear. I have written it in a congested way. So what I'm doing is I'm taking the denominator as n. It will be n minus 5 as I have taken out. So these two terms are written over here, and this term I have written as it is. All right. So again, this will become n minus 5 by n into 1 minus 5 by n times summation of j not equals to I Sj. Okay. So this is utility of player I when player I is playing 1 and all other players are playing SI star or sorry S minus I. Is this clear? So these two are the utilities. This is one utility and this is the other utility. Is it clear?
Yeah. So this is matching the previous one that you did just before that, when you did the general expression.
Yes, over there we had a
No, not that slide.
Which one?
No, on the same slide.
Yes.
This
Yes,
just before
yes.
writing this rate, you wrote that, no? That one,
Yes,
the
yes.
upper one.
This will match. So you see what is happening. I'm taking n as the denominator for 1 and this. So it will be n, and this is minus 5. So n minus 5 by n times 1. It will match. Just do this. What is this? This is 1 minus 5 by n times 1. These two are there, and then 5 by n. So this will come 5 by n times j not equals to I S j. Right. So this is that this part. And this when you take the denominator n minus 5 times 1. Any doubt?
Yeah, my doubt was how come there you did a general thing where 0 and 1 both were getting included, while here we are getting it only for 1.
Actually, in this expression, if you substitute Si as 0, then this term will become 0. So it is 0 minus 5 by n times summation.
Actually, there Si is anyway equal to 0, so 0. J not equal to I. Okay. Okay, yeah. So here it is Si equal to 1 in there. So to that extent it is different. Understood. Fine. Yeah.
So I'll just rewrite this expression again. So we have x ui when 0 and s minus I. It is actually 0 minus 5 by n summation of j not equals to I Sj, and ui 1 comma s minus I. It is what? N minus 5 by n times 1 minus 5 by n summation of j not equals to I Sj. These two are the utilities of player I for the strategy 0 and 1. And you see, this utility will be same for all the other players because this is a symmetric game. All the other players will have similar utility. Is this correct?
Yeah.
Right. Now you have to obtain the best response of each player, and then we'll see what is the intersection of those best responses. All right. Now over here, you see when 5. So we'll take this division. N is greater than 5 and n is less than 5, and then it will be more clear. All right. So first, if n is less than 5, when n is less than 5. So you see when n is less than 5, so this will be negative. The first, so I'll just write 1 and 2. When n is less than 5, 1 is negative. Any doubt in that? It is already negative. It doesn't matter n is greater than 5 or less than 5. First will always be negative. Is this clear? First expression will always be negative.
Yeah.
No matter what value of n is. The second expression will change. You see when n is less than 5, suppose n is 4, so it will be 4 minus 5, which is minus, and this term is already in negative, and this term will always also become negative, so this will also be less than 0. Again, check clearly. When n is less than 5, this term will be negative. This term is already negative. Therefore, the second utility will also become negative. Any doubt? So the first utility is also negative, second utility is also negative. Is this clear?
Yeah.
Roshni, are you following? Okay, I hope it's clear, and if not, you can just ask me in the next class. So you see, in both the cases, it is negative. Now, when will this utility be? So I should write
N greater than 5, no?
No, that is not I'm saying. I'm saying that it should be equals to 0 because this SJs can be 0. All the other players can play 0. It can either play 1 or 0. So it will be less than equals to 0. So this term will either be 0 or negative, and this term will either be 0 or negative. Am I correct?
Sorry, come again.
So what I'm saying is, I'll just erase this again. So you see, when this term, when SJs are 0, all the other SJs are 0, then it will be less than equals to 0, because it can be 0 as well, right? Because this term can be 0. This summation SJs, when all the other players are playing 0, then this term can be 0. When to this term, so you see this term is 0, but this term is negative, but this term can be 0. So this is always less than 0. It will not be equals to 0, because this term is always negative. No matter what this value is, either 0 or negative, it doesn't matter. This term will always be negative. Yes. Therefore 2 is always less than 0. So you see, there is one value where the utility becomes exactly 0, not negative. What is that value? When all the players are playing 0 for all I. For all I, when all the players are playing 0, that strategy, when all the players are playing 0, then this utility will be the utility of all the players, and that will be 0 and not negative. Because you see, if any other strategy is being played, either one, even for one of the player, the utility of all the players will become negative. So the best strategy of all the players is to play 0. Is this correct?
Yeah. So we have to write UI equal to 0 if all SI equal to 0, right? You have written SI equal to 0.
UI is equals to 0 for all SI is equals to 0. Yes. So I was saying that SI will be 0 for all I.
For all I. If SI is equal to 0 for all I and utility is 0.
Utility will become 0.
And that is the best response.
That is a Nash equilibrium. Pure strategy Nash equilibrium. Why? Because this is the best they can do. When n is less than 5, what is the best they can do? They can
when n is less than
their
5.
Utility. Okay. They can make their utility 0. They cannot make it positive. So the best they can do is make it 0. Right?
Understood. Yeah.
Now the second case, if n is greater than 5, you see this term. So I'll write it as A and B. This term is positive. Right? Term A is positive. When n is greater than 5,
positive. Yes.
Term A is positive. Term B can either be negative or 0. Now you see
0.
You see this Sj. If n is greater than 5, suppose n is 6, and this Sj can take either value 0 or 1. So when n is more than 5, when it is 6, this sum will always be more than 6, always be more than 5. Because we are not including I. When we are not including I, so what is Sj? Summation of j is not equals to I is S1 plus S2 plus ... We will not include Si. All right. Si plus 1 plus ... Sn. Is this clear? When n is more than 5, which is actually, suppose n is 6. So this term, this sum will have 5 terms because Si is not there. When n is 6, Si is not there, this term will have 5 terms.
Yeah, this term will have 5 terms.
If I'm confusing you, just
no, I'm not confused. It will have 5 terms. I understood.
Terms,
so
right? Okay. So this term will either be 0 or it can be positive, right? Or it can be either be 0 or negative. Term B will either be 0 or negative. Term A will always be positive because this n is greater than 5, right? Now you have to see what will be the summation of term A and term B, because term A plus term B is the utility of player I when player I is playing 1 and all the other players are playing Si minus 1. That is why I was talking about, let us see what is happening when n is 6, 7 or 8. We have to take the sum of a and b. Is this okay? Because a plus b is the utility of player I when he is playing 1. Before that, what is happening to this term? Number 1, it can always be less than equals to 0. This is fixed. This is fixed. Now, if this term b can take value 0, but a can take value greater than equals to 0. So term 2 can be positive. Term b can be 0 when all the sj's are 0.
I think we went a bit too fast. I was there with you when, let's say, okay, when n equal to 6, you said this.
Let us just make this simple. I have to make this a little bit complicated. Let us make this simple. So this is clear, right? When n is less than equals to 5, what happens?
Yeah, that is clear.
That is clear. So we'll just move again. So we are calling this term 1. Term 1, this is term 1. And term 2 is actually summation of
A and B. Yeah, I understood that part.
So if n is greater than 5, so what happens to term 1? Doesn't matter, it will always be less than equals to 0.
No, positive. Term 1. Term 1 will be
Term 1?
less than.
Now for term 2, we'll have to see A and B.
Yeah.
So A is always positive.
A is always positive.
B can either be less than 0 or negative.
It can either be 0 or negative. Correct. Yes.
Correct?
Yeah.
Now you see, when this term Sj, summation of Sj, can take value maximum, it can take value maximum of n minus 1.
Yes.
It can take a maximum value of n minus 1.
Yes.
Or small n minus 1. We have small n minus 1. So what will this value be? It will be minus 5 by n times n minus 1 at max.
At max, yes.
Term B. And what is term A? Term is actually n minus 5 by n, and term B is at max minus 5 by n times n minus 1. Right?
Yeah.
So we'll just solve this and then we'll see what happens. Denominator is n. We have n minus 5 minus 5n plus 5. Alright? I have done it correctly. If this cancel out, it becomes minus 4 by nn. So it becomes negative minus 4. So a plus b will be negative. Will be negative. Is this clear? I have done it simply. I am trying to do it a little bit simply. You just see at max, maximum value b can take is this. Will either be less than this or this, right?
Yeah, so this guy, when he's playing 1, n minus 5 by 5, n, right? And at max is this, so even then it is becoming negative. But there will be some cases where this guy will be.
That is where I am coming. That is where I am coming. Now, at minimum, b can be 0.
At minimum,
at
b can
minimum,
be 0.
b can be 0. At minimum, b can be 0. When b is 0, then this term a plus b is positive.
Yes.
So again, you see Si is equals to 0 is the strategy where it will become Nash equilibrium. Si is equals to 0 is actually the Nash equilibrium. When b is equals to 0, then this term becomes positive. Otherwise, it will not. It may, but that is the best they can do.
So what you're saying is at times it is greater than 0, at times it is less than 0.
Yes.
But hence we are assuming when
not
SI
assuming,
is equal to...
we are not assuming. We are saying that you see in first term, this term A, term 1 will always be 0 when SI is 0. SI, all the SIs are 0. Right? That is the discussion was earlier. That discussion was clear. When SJs are 0, then first term will be 0. Utility of first term will be 0. So whenever all the players are playing 0, then utility from first term will be 0 and utility from second term will be positive. So everyone will try to play 0. Because either they will obtain 0 or positive, never negative. They will either obtain 0 or positive, not negative. Is this clear? When everybody is playing 0, this term 1 will be 0, term 2 will be positive. Clearly it will be positive. So everybody will play 0. If someone plays 1, then there might be cases when this A plus B becomes negative. Therefore, everybody will try to play 0. You can ask me doubts.
No, I'm just processing. What you're saying is, in the second term, if someone plays 1,
yes,
then the term B may become negative because it will be sum of 1s. And hence the term A plus B less than 0 may be possible.
Yes.
But A plus B is also greater than 0 when,
when
all SJs are 0.
No, not only when. So suppose some of the SJs are 1, then also it can be positive. But in that case, utility UI when player I is playing 0, this term can become negative, right? Will become negative. This utility will become negative.
No, we are talking of second term.
Yes, second term.
B.
So there are some cases where it will be positive. There are some cases when it will be negative. But for sure, if everybody is playing 0, for sure it will be positive. No doubt about that.
If all Sj is 0, term 2 will be positive, yes.
Yes, the term 2 will be positive and term 1 will be 0. There is no ambiguity in that.
Correct.
Therefore, it will become Nash equilibrium. That is the best they can do. Because if somebody plays 1, term 1 will become negative.
No, but SJs are playing 0, but SI is 1. He's playing 1. In term 2, we are saying all SJs are 0.
Yes.
But UI, SI is 1.
1, yes. Yes, and okay. So you're saying SI, okay.
So term A will be 1, because all other guys are playing 0.
Okay, right. Right. So what I'm saying is, again, I was wrong. What happens now is, you see, when player I is playing 1, then term 1 will be negative, because when
he's playing 1, we are talking of term 2.
Yes, we are talking about term 2, correct?
And n is greater than 5, then term A in term 1 is positive.
Term A, yes, in term A, in term 1 is positive, correct?
So,
correct. So I guess I was wrong. So in that case, everybody play 1. I guess
no, but everybody plays 1, so then A plus B will become less than 0, because the left hand side, the term B will become
yes. Negative. I will check again. I will check this again.
So there will be a point where it will transit from positive to negative.
No, I will check again. Where the doubt is, I will just check again. Again, there is one interesting thing. What happens is, when if n is equals to 5, exactly equals to 5.
Let's see. Maybe at that point it may, but n is equal to 5.
When n is equals to 5, what happens is, this term A becomes 0.
Term A becomes 0. Then it is collapses to the first term.
Yes, when it collapses to the first term, then it says that everybody should play 0. Because
everybody should play 0, yeah.
I will just check what happens when n is greater than 5. I have got confused. Okay.
Yeah.
So this was the last problem, and I had kept this part, but I guess if you have doubt in this part, then only we'll discuss, or we can just conclude. I will take this problem again in the next section, and then we'll proceed.
Okay, fine. I somehow didn't get the mail of the last Friday, so maybe I'll check the video again. Then if there is something, then I'll loop back.
Sure, no problem.
Yeah, okay.
So yeah, so I apologize for this confusion over here. I'll just check.
Yeah, okay. You are saving
Alright.
it as annotations, right? Yeah.
Yes, I'll just save
Okay,
everything just now.
Yeah, okay.
Okay, so do you have any doubt in this or not? Duopoly?
No, Cournot, I have to brush up my basics over here. Because I have not yet finished completely the entire week 2. So
Okay,
because the
but
assignment
Cournot
deadline was.
Cournot was discussed earlier than mixed strategy Nash Equilibrium.
No, so I have not yet finished week 2. So in week 1 it was not discussed. I still have to finish week 2, so I'm not very sure.
Okay, so if you want, I can just quickly
tell
you what Cournot duopoly is. So just
okay.
Let me take the example what sir has given. It will be quick. 1 minute. Okay, so what this says is, suppose there are two firms and both these firms are producing goods which are actually switchable, so substitutable. So it can be either same good or substitutable good like tea, coffee or something like that. And they are trying to finalize the production quantity of these goods. So let us say the production quantity as S1 and S2. Alright, so and this can take Si can take value between 0 to infinity, anyway, not infinity. So when you write infinity, you shouldn't write this closed bracket, it is open bracket. So it will be open bracket. Alright. So when these two firms are deciding what should be the production quantity. The price of this product actually depends upon the total quantity available in the market. So it is given as A minus B times S1 plus S2. So there are two players. Therefore, the price is coming out to be A minus B times. So more the quantity in the market, the less is the per unit price.
Yeah.
All right. So
A and B are constants.
A and B are constants. And cost of production for firm 1 is actually given as CI is given as it is just constant C for per unit, so it will be C times SI. So this cost, this is capital C. Cost of production is given as a fixed cost C times the quantity he is producing. Very simple expression. Fixed cost into the number of quantities. Therefore, the profit of the firm, so you can write it as U utility. In actually operations research, it is written as pi. So UI is dependent upon S1 and S2 because this P is dependent upon S1 and S2. This profit is given by revenue minus the cost. The revenue will be A minus B S1 plus S2. So this is the per unit price times the quantity he is producing minus cost. So this is SI. Is this clear?
Yes.
So this will actually become A minus C minus B times S1 plus S2. And here I have just written capital C, don't be confused. Just let it be. And this will be SI. Now you can just write the utility of both the forms. U1 will be S1 comma S2, which is A minus C minus B times S1 plus S2 times S1. And U2 will be S1 comma S2. A minus C minus B times S1 plus S2, and this is S2. Now you have both the utilities, you can just differentiate and you will obtain the values of S1 and S2. So what you have to do is you have to obtain the value of that best response of firm 1 given a fixed response of firm 2. So you will partially differentiate this term, and again you will partially differentiate this term. When you partially differentiate, you will obtain S1 star, which is the best response of firm 1 as A minus C, A minus C minus B times S2 by 2B And similarly, S2 star will be given as A minus C minus B S1 by 2B. Now you see, this best responses actually depends upon the strategies of the player. So S1 star depends upon the strategy of S2 and S2 star depends upon the strategy of S1. Now, to obtain the Nash equilibrium, the best responses should intersect. So we'll say all the players are playing their best responses. So this will become S2 star and S1 star. And then you'll have to simultaneously solve these two equations.
Okay.
Is this clear?
Yes.
Now when you simultaneously solve these two equations, the solution will be S1 star is equals to, it becomes A minus C by 3B, and same as S2 star becomes A minus C times 3B. So this is the Nash equilibrium point. This is the Nash equilibrium point.
Okay.
So the Nash equilibrium is A minus C by 3B, A minus C by 3B. Now sir has taken one example when he's saying that A is 10 and B is equals to C equals to 1. And for this he has drawn a graph. So what is that graph? You see, we have best response lines. So you see, when we discussed this Nash equilibrium and mixed strategy Nash equilibrium, we had drawn the graph of this or plot of this best response curve. So we have the best response curve. S1 star is actually equals to A minus C minus B S2 by 2B. Similarly, S2 star is A minus C minus B S1 by 2B. If you plug on these values, it will become 4.5 minus half S2. This will become 4.5 minus half S1. Is this clear?
Yeah.
So you can just plot the best response curve similarly to what we have done. It will be 5, 10, 10. This is S1 and this is S2. So you see, S1 star gets this value when S2 is 0. Then S1 star is 4.5. When S2 is 0, then S1 star is 4.5. When S2 becomes exactly equal to 9, then S1 star is 0. You just put 9 over here, you will obtain S1 star as 0. So this will be the line. I'll just take a different color. This will be the line joining. So this is the best response curve for player 1. Again, when S1 is 0, S2 star is 4.5. This is 4.5. And when S1 is 9, S2 star is 0. So this is the line. I'll just take another color. So this is the best response curve. And this is the Nash equilibrium which we have obtained. So if you plug on these values, 10 minus 1 by 3, which is actually 9 by 3. So this is 3, 3. So this is the Nash equilibrium for this problem.
Yeah.
Is this clear?
Yes.
Now, sir has also discussed some part on dominant strategy and how this Nash equilibrium is self-enforcing. So you see, when player 1 plays any value between 0 to, suppose, any value, infinity, 0 to infinity, the best response of player 2 will always be between. So suppose player 1 is playing 0, the best response for player 2 is to play 4.5. When player 1 plays any value above 9, the best response of player 2 is to play 0. So the best response of player 2 is in between 0 and 4.5. No other value is there, which is the best response to any other strategy of player 1. Is this clear?
The graph is basically, that graph is the.
Yes. So if S1 is in between these 2 points, then it will be between these lines, these points. S2 will be between these points. And any value above 9, it will always be 0. So it is again, S2 is in between 0 and 4.5. Therefore, this part or any other part, this area is a dominated strategy of player 2. Dominated by this part, 0 and 4.5.
Yeah. Okay.
Any strategy above 4.5 is dominated by this strategy. Similarly, for player 1 also, this is a dominated strategy for player 1. So he will only play values from 0 and 4.5. No other value he will play. Is this clear?
Yeah. So this area is the one which is under play.
Yes, this is the important part now. Now, if you apply this concept again, suppose we are saying that the game has been reduced. Now the player doesn't play from 0 to infinity. The player plays from 0 to 4.5 because the game has been reduced. He will not play any value more than 4.5. Now you see this graph for player 2 is in between these two parts, these two lines, right?
Yeah.
This is the best response of player 1. So the best response of player 1 will always lie between these 2 points. Always lie between these 2 points. Because these points will be dominated. You see, the graph is reduced. We are in this rectangle. We don't worry about this part. We are only worrying about this smaller area. Is this clear?
Okay.
So the best response of player 1 will only lie between these 2 points. Similarly, for player 2 as well, it will lie between this and this. So it will only lie between these 2 points. So this is also dominated strategy. Is this clear?
Okay.
Now you can further reduce this again. So you see, in this reduced game, the dominated strategy, so the best response of player will lie in between these 2 points, and this is dominated strategy.
Sure.
And from player 2 also, this is dominated, and it will only lie in between these 2 points, this point and this point, this point and this point. Is this clear? So you can further reduce this game again and again, and eventually you will come to the Nash equilibrium.
Circle 2, 3, 3. Okay.
That is what sir has explained in this.
Okay.
And there is a little more concept about shifting to the best response. You can just watch the lecture. If you have any doubt, you can ask me in the next lecture.
Yeah. Okay.
All right. Thank you.
Okay. Yeah. Thank you. Thanks a lot.
So yeah. So I'll just conclude. So I am just Shubham Keshri.
Yes.
I am doing PhD in Management Sciences at
IIT Kanpur. Okay. And you're along with that other TA, Aarti.
So Aarti is actually in some other department. My department is Management Sciences. My area of research is Operations Research, and I am not exactly working in game theory. I have studied this course as my coursework. My area of research is integer programming and heuristic and algorithm development and so on.
Okay. Okay. Thank you.
Thank you.
Thanks a lot. Thank you.
No problem.